Kia ora. Today we're going to have a look at the 2020 probability distributions paper from NCEA. I'm going to be going through this paper at a standard pace, I would say. I will try to explain each question as we go. I will be referencing the formula sheet, and I will also be using a graphics calculator. So I will be, any time that I can use the graphics calculator, I will use that instead of tables, instead of manually doing calculations. So yeah, cool, let's get started. So let's go down to question 1A. 1A. A hospital aims to deliver lunch, the midday meal, to patients anywhere between 5 and 25 minutes after the meal has left the kitchen. They also aim to deliver dinner, the evening meal, to patients anywhere between 5 and 30 minutes after the meal has left the kitchen. Sketch the two probability distribution models for lunch and dinner on this grid. Clearly identify which is lunch and which is dinner. Okay, cool. So for this, what I am going to do first is pretty much working out what distribution it is probably the most important part of this external. So whenever they give you two numbers, a minimum and a maximum, and no other details, you know that this is the rectangular or uniform distribution. Alright, so I'm going to be drawing two rectangles. So the first thing you're going to have to do with a rectangular distribution is work out what the height of those distributions is going to be. So we've got two models here. We've got the 5 to 25, and then we've also got that 5 to 30. So in order to find out what the height's going to be, we're going to have to find the range. So for our first one, it's 5 to 25. So that means that it's 20 in total. This one is from 5 to 30, which means it's 25 in total. So we're just looking at the total range. Maybe I'll just do a T here. Right, now if that's the total range, then the height is just going to be 1 over those numbers. Okay, so I'm just going to draw their grid. So our minimum that we're going to need to show on here is going to be 5. 5. Yeah, probably can go up like that. 10, 15, 20, 25, up to 30. So this is where I'm going to do my distributions. The most important thing is see how I've got a overall minimum of 5 and an overall maximum of 30. I just need to make sure that my grid spans over those numbers. Okay, so we're going to do 1 over 25 and 1 over 20. So let's just type them in and get some decimal values for them so that we know the heights. Because fractions are sort of hard to know how tall they're going to be. So 0.05, and then we've got our 1 over 20. So we've got 0.04 and 0.05. So what I'm going to do is I'm just going to make this like that. I'm going to go 0.5 and 0.4. So these are the two heights of my distribution. So the one that is longer, right, so it goes from 5 to 30, which has a range of 25, it means its height is going to be 1 over 25. So maybe I should actually write that over here, 1 over 25, and then this is 1 over 20, just so I know which one. So let's do this first one first. So it starts at 5 and it goes to 25, and its height is 1 over 20. So 5 goes up to 1 over 20, or 0.5, and it goes across to 25. That's the first rectangle. The next one, it starts at 5, so I'm just going to use that same line, but this time its height is 1 over 25, or 0.4, and it goes across to a maximum of 30. And there you go. They also said to clearly label. You've got to be really careful with these distribution papers. They want you to clearly identify which is lunch and which is dinner. So dinner was the one that can be longer, so I'm just going to put my dinner label here, and then I'll put my lunch label just here. I think that's pretty clearly labelled. They might want something better, but I think we'll be fine. Okay, cool. So that's 1AI completed. So let's go to 1A2. Meals are cold if they arrive more than 20 minutes after leaving the kitchen. Using appropriate probability distribution models, calculate an estimate for the probability that a patient has both a cold lunch and a cold dinner on the same day. Okay, so 20 minutes. I'm going to draw one line going up here. So this whole region here for lunch is cold, and then this whole region here for dinner, notice I'm only going up, notice I'm only going up to that line. This whole region for dinner is cold. Right, I'm just going to make that lunch one a little bit clearer, that that's on its own. Okay, so to work these probabilities out, remember the total area of any distribution is equal to 1, and we're just pretty much finding a proportion. So we could actually just know what these are, because I can see that it's a quarter of lunch that's shaded, and I can see that it's 2/5 of dinner that's shaded. But that's just, sometimes it's good to know what you're working towards, or what sort of what you expect that the answer is going to be around about. Okay, so I can't remember how they actually want you to do these calculations, but what I'm going to do is just find the area of a rectangle. So you can see that the base here is 5, so let's just go P that lunch takes longer than 20. So that's going to be the base, so 5 times the height, which is 0.5, and that comes out at 0.25, a quarter, just like we thought. Cool. Then the probability that dinner is greater than 20 is going to be the base, so that's going to be 10 times the height, which is 0.4, and when you look at that, it ends up being, whoa, what did I do wrong here? These are wrong. My bad. I'm going to just join these together. I by mistake didn't put a second 0. I'm sure you guys noticed that in the video, but we do make mistakes. Everyone makes mistakes. That's why you've got to check your work. So 5 times 0. That should have been 0.05. You get really good at correcting your working if you do this for long enough. And I'm just going to make that into a 4 again. Times 0.04, and then that's going to get us to 0.4, which is 2/5. So there you go. Let's just read the question one more time. Calculate an estimate for the probability that a patient has both a cold lunch and a cold dinner. Ooh, both a cold lunch. So they just made this into a merit question, right? So anytime that they do two events that are supposedly independent, you're sort of thinking the logic of a probability tree. So it's you're going to have lunch first, and then you're going to have dinner, right? So the logic is that lunch, it can be cold or not cold, and then dinner can be cold or not cold, right? So all we care about is the branch of both a cold lunch and a cold dinner on the same day. So cold lunch is 0.25, and then cold dinner is 0.4. So you're just multiplying those probabilities to get cold. Right, so it's going to be 0.25 times 0.4. You don't have to show this. I'm just sort of trying to give you some understanding. But you just have to show this calculation here. 0.25 times 0.4 is 0.1. I think that's it. Maybe it's worth sometimes making it clear to the marker what the heck you're actually doing. Both cold. Cool. Let's move on. Question 3. So we are doing 1A3. Consider an assumption you made when you calculated your answer to part A2. Discuss whether or not this assumption is likely to be valid. Okay, So when we did this calculation, we had an assumption. I think there's only one really clear assumption, and it's that your lunch being cold and your dinner being cold are independent. I assumed that my lunch, I should say there, that a patient, gotta make the context right, lunch being cold is independent. This is where you get the mark, writing that word there, of their dinner being cold. This is the assumption. It's independence, and remember, independence means that this event happening does not affect this probability of this event happening, right? That this being cold will not have any effect on that being cold, and vice versa. Now, we now need to discuss whether this assumption is likely to be valid. This is probably not valid, as the same kitchen staff are probably working. During lunch and dinner on a given day. So these answers, generally there's not like a set answer that you have to go with, but you just have to have like common sense, really. So the buzzword is using this word independence, and then you've just really got to think in context why that might not be independent. So I've sort of come up with this one, that the same kitchen staff are probably cooking during lunch and dinner on any given day, and if they are slow during one meal, they will probably, actually I shouldn't have said kitchen staff, because the kitchen staff is actually, I should be saying serving staff, because the question actually sort of said that the dinner had actually already been cooked, right? So it's the delivery. It's the delivery we're looking at. So I'm going to go with serving staff. Yeah. They will probably be slow during the other. Yeah. So pretty. Yeah. Is that a good reasoning? So maybe some other reasoning I could go for would be that an individual patient, so there might be a priority patient, so like priority patients will, so say you're a priority patient for lunch will also be priority for dinner. So that's a totally different reason, and I'm just gonna, sometimes it's safe to like give a couple of reasons, because one of them might be correct and the market might say yeah, that one's good, and the other one might not be. So yeah, so maybe you're a priority patient who needs to get their meal at an exact time. So if you get your meal at an exact time for lunch, that means that chances are you're going to be also getting your meal at a better time for dinner. So both your lunch coldness and your dinner coldness are going to be very low. Yeah, too long on that question. Okay. B. So we're up to 1BI. In New Zealand, the Ministry of Health recommends that all adults eat at least 3 servings of vegetables each day. Suppose that the number of servings of vegetables eaten by New Zealand adults each day can be modelled by a Poisson distribution with lambda being equal to 3.2. Use this Poisson model to calculate an estimate of the proportion of New Zealand adults who eat at least the recommended number of vegetable servings each day. Okay, first of all, this is strange that they're telling you what distribution it is. I think usually in an exam they don't do that, but I guess they do now. Sweet. Well, that's easy as. We already know exactly what we're doing. So I can go straight into stat. I can go straight into distribution. I can go straight into Poisson, but I don't quite know if it's a Poisson point distribution or a Poisson cumulative distribution. So we've got to try and work that out. But I might put first of all that lambda equals 3.2 critical information. What do they recommend? Recommend at least 3. At least 3. Those are the important pieces of information that I can see. Use this model to calculate an estimate for the proportion of New Zealand adults who eat at least the recommended number of vegetable servings each day. So we're looking at the probability or proportion this time of this distribution. So this is the people eating adults that has been modeled by this lambda equals 3.2 with Poisson, and we want to know when that number is at least 3. So I know it's going to be with a 3, right? And I want this group to be at least this number. So the crocodile is going to eat the bigger group. So we want the adults to eat. So sometimes I like to think of the numbers. So maybe like, does an adult that eats 2 servings, are they going to fit into this? No. Right? We want at least 3. So an adult that eats 3, 4, 5, 6, 7. So the crocodile is going to eat this side, right? And because it's at least, that means we have to also have an equals involved. So that means that probability that x is greater than or equal to 3. So this is what we're looking for here. Now, sadly, cumulative, it pretty much means, so that PCD there, that PCD means cumulative. That's what the C stands for, pretty much. And that actually means up until, right? So that means you can do the probability that x is less than or equal to some number, right? So our calculator can only work out that, and that's not this. So we're going to have to do, do I want to show you? I might explain this now. I'm going to explain it now. So let's say we had our distribution of people eating, and it looks something like, I don't know, something like that. So that's 0 servings, 1, 2, 3, 4, 5, 6, 7, da 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 da. Poisson goes on forever. Right? We're looking for these adults that are 3 or more. So it's the adults that eat 3, the adults eat 4, they eat 5, they eat 6, 7. We're looking for this, but cumulative can only do up until. So it can only do 0, 1, or 0, 1 and 2, or 0, 1, 2 and 3. So it can only do some number and everything under it. So we can actually find out this one by just doing the reverse, because cumulative we could do zeros, the 1s and the 2s, and because we know that all distributions add up to being 1, we can just do 1 minus whatever we find in the red. So let's write that out. And we're going to go with that this here is equal to 1 minus the probability that x is whatever this thing is here. So it's the number 2, and we're including 2 and everything below 2. So it's just going to be 1 minus this thing here. So I'm going to do that in red, because that is what we find over in red over there. Alright, and then that will find us this answer. Okay, so we go into our calculator, PCD now. Remember, you just have to change data over to variable. You never actually do data list, so it's kind of annoying that that's the default setting, but it's probably useful for something. So now we're doing 2 or less, so that's everything up until 2, so x is 2. And our, again, why did they make that a mean when they could have just made it a lambda? Maybe the calculator doesn't have a lambda symbol. Anyway, lambda was 3.2. So it's going to be 1 minus 0.3 0.3799, and that is going to be 0.6201, and that's our answer there. Okay, what would the value of lambda need to be so that under a Poisson model at least 95% of New Zealand adults ate at least one serving of vegetables per day? Dang it, that's a mean question. Putting at least that and then putting at least again is confusing as heck for us dyslexic people. Actually, no, dyslexia actually affects that at all. Okay. At least 95% of New Zealand adults ate at least. How do I get understanding for you guys on this one? So this is an excellence question. Whenever you have to find a lambda, this is going to be the excellence question. But when you want to find, if you have an unknown lambda, right, you always need to know the probability that x equals 0. So that's what you're going to need to have. So we need to find out how we can find that. So if at least 95% of New Zealand adults ate at least one serving, so that means we know that px of at least one serving, so that means 1 is the least, so they're going to eat that one instead, but it includes 1, equals 0.95. So we know that. So that means on our picture it would be 1, 2, 3, 4, 5, 6, 7, 8 is 0.95. Well, then that means whatever's left over is just going to be 1 minus that 0.95. So px equals 0 is 1 minus 0.95. So that means it's 0.05. Okay, so we now know that probability that x equals 0 is 0.05. Now let me just get the formula sheet out for you guys. So the formula sheet is going to be useful here because we need to have the formula for the Poisson distribution, and here it is here. So that's given to you in the exam, so you can learn to just use this. No problemo. So I just want to get it because in a nice spot so we can manipulate it. Oh, wonderful. No, I want better than that. Oh, yeah. Okay, so we know that the probability that x equals 0, so I'm going to do this particular example, is equal to lambda to the power of x multiplied by e, which is just a number, to the power of negative lambda over x factorial. In fact, we now know that little x is 0, so I'm actually going to make that little x 0, and it's over 0 factorial. Right, this is also little x, this is little x, and this is little x. So this is enough information nearly. I didn't make that 0 clear enough at all. Colour it in there. Beautiful. Okay, now what do we also know? We know that the probability that x equals 0 from here is 0.05. So I can put that in over here, 0.05. So now all I'm going to do is I'm just going to do some algebra on this part of it. Right, that equals this. That's enough information for me to find out what lambda is equal to, or what these lambdas are equal to. Okay. What did I do wrong? My brain's not happy for some reason. Lambda to the power 0. Okay, cool. What you need to know for this is that anything to the power of 0, or most things to the power, the vast majority of things in this universe to the power of 0 is equal to 1, and also that 0 factorial equals 1. That's all you need to know. Alright, because then therefore this lambda to the power of 0, let's write it out again, lambda to the power of 0 is going to be 1, and then it's going to be 1 times e to the power of negative lambda, and then on the bottom 0 factorial is also 1, so we put a 1 down there, and that's equal to 0.05. from there, we now know that because 1 times anything and anything divided by 1 is just itself, we now know that e to the negative lambda, look at that, no more fraction anymore, equals 0.05. Now you just need to know another fact, that the natural logarithm is just it's a way of writing log base e, right? And the reason, and because it's log base e, it actually gets rid of e to the power of, right? Because logs are a way of getting rid of exponents, and the base being e means that it matches up with this, the base of this power being e. So it just cancels out. So pretty much if we do ln of this side, it's going to get rid of that e to the power of. So then if I do ln of that side, I'm going to have to do ln of this side. So ln of 0.05. So all that's left on this side is negative lambda. These cancel out. Negative lambda equals ln 0.05. So let's type that into our calculator. So we need to do ln of 0.05. And that's going to be negative 2.9957. So then these negatives cancel each other out. So then lambda is equal to about 3. Just because that number's, let's say I was doing 2dp, that would be a 3, and that's a pretty number. I mean, which number's actually prettier? They're both equally numbers, unless you're dealing in discrete distributions. Anyway, what would the value of lambda need to be? So blah 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 blah. Yeah, done. Excellent. Boom. Okay. Give 2 reasons why the use of the Poisson distribution may not be appropriate. Oh, they're giving us another shot at excellence here. Maybe this is more of a merit question. Okay, so with these ones here, so this is 3, was it B2? I think so. 3B2. Okay, 2 reasons why Poisson may not be appropriate. So for Poisson, I remember Poisson. And what I do with that is I know that it's proportional. The reason it's proportional is that when, so say it's like the chance of an earthquake happening like the amount of earthquakes that happen per year is 3 in this random obscure country. If it's every 2 years, proportional just means we just double the 3 for 2 years. O, I do for occurs randomly. The idea of the Poisson distribution is it's a way of modeling rare events. So I should actually say rarely. It occurs rarely. Yeah, it's the whole idea of the distribution is for rare events. The I is this independence. So events need to be independent of each other. Then with these S's are simultaneous. So I'm going to put simultaneous, and I use all of these other letters as well. Simultaneous occurs never. Right? So these are, I do all of these ones together. So this is how I remember Poisson. It's proportional, it occurs rarely or randomly. I is independent events, and simultaneous occurs never. Okay, which of these are not? So they're asking us to be critical, right? They want us to see where the distribution falls short. So in our example, we're looking at vegetable consumption in adults, right? Which one? This situation. Yeah, okay, we'll just go with this one here. Okay, so they're using it, the number of servings of vegetables eaten by New Zealand adults, modeled by Poisson. So this is what we're trying to critique here. So we've got to think, is it proportional? Are we going to, if it was 2 adults, would it become 6.4? Yeah, so proportional is actually kind of hard to critique here. So we'll have to move on from that. Occurs rarely. So this is a really easy one to pick up on. So eating vegetables is not a rare event. Adults will be eating vegetables every day. Pretty much. So Poisson doesn't. What are we actually arguing? We're saying, was it just not? May not be appropriate. So Poisson may not be appropriate. Pretty much, you are, when you're answering these questions, what you're trying to do is you're trying to use these are the buzzwords. So I need to say the word occurs rarely or occurs randomly. So I've said that is not a rare event. Then you need to do context. Adults is the eating vegetables. So I need to do the context, and then I need to add a little bit of logic. They're eating them pretty much every day, so that defies it being a rare event. And then I just, a little conclusion. Okay, so that's one reason. What do they want? Two reasons. Independent events. Okay, this one's pretty. This is one reason. Two reasons. Generally, if a meal has vegetables in it, has a vegetable in it, there will be other vegetables. Yeah, this one's like too easy to defy it being Poisson. So I've given context now. I need to make sure I'm saying independent. Therefore, vegetables being consumed by adults is not independent. This is probably actually a better argument for simultaneous. I'm probably actually arguing not independent. So I'm just going to do both at once, independent and it fails on events not being able to occur simultaneously. I think I spelled simultaneous wrong. Whoopsies. Simultaneously. So I'm just going to do both at once because they only want two anyway. I'm sort of ticking two boxes here. It fails on events not being able to occur simultaneously as well. And then maybe I'll just give an example. Salads have many vegetables inside of them. Yeah, this is a horrible situation for Poisson. Okay, let's move on. Give two reasons. Yeah, that's what we just did. Okay, dang, we're only up to question 2. Are you freaking serious? Do I make a separate video? It's kind of smart. Nah, it's probably better if it's all one video. Then I'll just label them right. Okay, hopefully I can pick up my pace. Okay, 2. AI. It has been estimated that breakfast is eaten daily by 49.9% of New Zealand youths. Suppose that a random sample of 8 New Zealand youths was taken. Use an appropriate distribution model, calculate an estimate for the probability that less than half of these 8 youths ate breakfast daily. Okay, so we're going to play the game of what distribution fits. Now, first of all, it is discrete. 8. We're looking at 8 people and we want to know how many of the 8. If you're looking at individuals, it's discrete because you can't go with a half of a human or like 0.66321 of a human. So it's discrete, so it has to be Poisson or binomial. Now we've got a probability here and we've got a number of trials here. So when you've got P being equal to 0.499 and you've got N being equal to 8, it has to be binomial. Because binomial has those parameters and yeah, it's not Poisson, we don't have a lambda. Okay, pretty straightforward choice, I think. calculate an estimate for the probability that less than half of these 8 youths ate breakfast daily. P, x, and then half of 8, 8 over 2 is 4, so it's going to be Px is 4, so it's less than, so we want to know less than that. That was pretty straightforward. Yeah, the distribution being, whatever, being less than 4. Too easy. Now, our calculator can't actually do that, but our calculator can do cumulative. It can do up until a number. This is not quite up until a number. This is up until a number, but not including the number. So we're just going to write the number that's below it and include that number. So this probability that x is less than 4 is the same as probability that x is less than or equal to 3. Because let's think of the options here. This is the numbers 0, 1, 2, and 3. They are all less than 4. Whereas this one here is 0, 1, 2, and it includes 3. So these are the same probabilities. So that's what we're going to use. So we're going to go to statistics, distributions, binomial, cumulative. It's on variable. X is equal to 3 now. There are 8 U's, and the probability of each one is 0.499. Equals 0.3655. Okay, let's move on. A year 13 student says approximately 50% of youths eat breakfast daily, so 5 of the next 10 youths sampled will eat breakfast daily. Comment on whether the student is correct in this reasoning. This student represents 99% of students in their understanding of probability, to be honest. 5 of the next 10 youths sampled will eat breakfast daily. He's sort of correct, or she's sort of correct, or they're sort of correct, but this is a real bold claim. So 5 of the next 10 youths sampled will eat breakfast daily. We don't know that in a sample of 10 there is randomization. The whole point in having a distribution, oh man, if the student told me this in real life, I would love to tell them why they're wrong. So I'm just going to pretend I'm doing that. Okay, so I'm going to have a look at binomial distribution. I'm actually going to model the situation. So if we should go for 49%, but I want to just show why he is wrong with his reasoning. So he's saying that approximately 50%, so I'm just going to put probability to 50%, and he said that there's 10 youths sampled. So he's right. So you can see this is the distribution here. The chances are, if he does 10, the most likely event would be, so this 5 here represents this, it is the highest probability is that 5 of them will have done it, but you can't blanket statement it. This bar is not going all the way up to 1 and then everything else is 0. This is the distribution. This is literally the whole point we look at probability distributions, is that you can't just take an expected value and say that's the thing that's going to occur, because there is a 20% chance that it'll be 4 students, a 20-something% chance it'll be 6 students, but then it could also be 3 of those students. There's like over a 10% chance. So yeah, he sort of defies probability distributions. I'm finding this hard to answer because I don't know. Yeah, the whole point of the distribution is, okay, I'm going to disprove him in like an easier way. This is a way easier way to do it. So what we're going to do is we're going to go to distribution binomial. We're going to do a BPD. So we're going to say P equals 0.5, N equals 10. The probability that he is right, the probability that X equals 5. This is a way easier way to prove him wrong. Variable, no, get out of here. X equals 5. 10 students. We should keep that as is. It probably does that in the answers, but I don't really care. So I want to disprove him. So I need to use his reasoning. 0.2461. So if he is dropping blanket statements like a numpty, like the numpty, I should stop reading. He is. He won't go far. He shall be proven wrong. He has found the expected value, or mean, but his guess will only be right less than 25% of the time, as proved by the calculation above. Okay, get out of here. You're wrong. Okay, question 3. For New Zealand children aged 2 to 14 years, the proportion who eat breakfast daily is estimated to be over 85%, or to be 85%. A health worker observed that for groups of 10 youths, the variation in the number of youths who ate breakfast daily was much greater than the variation they observed for groups of 10 children. Comment on whether the health worker's observation can be justified statistically. For New Zealand children, the proportion who eat breakfast daily is estimated to be 85%. Health worker observed that for groups of 10 youths, variation in the number of youths who ate breakfast daily is much greater than the variation they observed for groups of 10 children. Yeah, that's statistical reasoning. I don't really like this question at all, because we looked at youths. What do we count youths to be? These are these people here. Oof, I don't know how to do this without doing some ugly calculations, like working backwards from expected value. The thing is, this distribution that they're giving for these children. Oh! No, yeah, this is fine. Oof! Okay, I'm going to go with children. N equals 10, P equals 0.85. Oh, right, now youths, we're going to stick with our old one of, let's say N equals 10, because that's what they want us to ask, right? Yeah. And P equals 0.499. So what we could do here is we can get our formula sheet, and I think it's over here. Yeah. So if it's binomial, they're both binomial, we can actually straight up work out the variations, because we know that sigma equals the square root of n times the probability, I don't like the use of pi, 1 minus p. Right, now what we can do is we can work out sigma for children, and so standard deviation just means spread outedness. It's a measure of variation, so we can actually just show that this sigma is less than the youth's sigma. So it's going to be square root of 10 times 0.85 times 0.15, and then sigma of youths is going to be 10 times 0.499 times 0.501. And then we just got to prove that one is bigger than the other. should be pretty straightforward. Squirt 10 times 0.85 times 0.15, and so the standard deviation of children is 1.129. So I may as well stick to 4dp. You honestly will get away with 3dp. I don't know why I do 4dp. And then for youths, it's going to be 10 times 0.499 times 0.501. By the way, I got that it's just 1 minus p. I'm just doing them in my head rather than writing out lots of working, just to try and save time. But you can use the full formula if you want. 1.5811. So therefore, you can do these fancy things. The standard deviation of youths is greater than the standard deviation of children. So there is more variation in youths because they have a greater standard deviation. I wonder if they want us to explain what standard deviation is. I don't think you have to because it's sort of assumed we know what the heck that is by now. Okay. Comment on whether it can be justified. Just remember to read the question. Support your answer. So I've supported the calculation here. I sort of needed to talk about the health worker. And I've given the reason here. Okay. Suppose the energy intake at breakfast for New Zealand male youths who eat breakfast daily is modeled by a normal distribution with a mean of 11,200 kilojoules and standard deviation of 2,230 kilojoules. Okay, normal distribution, because they literally say normal distribution. Oh no. This is our distribution. The mean is equal to 11,200. Standard deviation is 2230. It's all in kilojoules. I'll just remind myself of that. They want to know, has an energy intake above, that's all we want. So they want to know P, that X is above 12,800. So the mean's 11,200, so there's going to be a 12,800 around about here. 12,800, that's going to be our X value. And they want to know everything above that. So we can use our calculator for that. Go distribution, normal, cumulative. The lower bound is 12,800 up until infinity, but I don't have an infinity button, so let's do a bunch of 9s. 20 to 30 is our standard deviation, and 11,200 is our mean. 0.2365. I don't think you guys need me to explain much more about that one. It's a fairly straightforward question. If you're stuck on that, you should be practicing your other stuff, I think, before you even jump into the exam. You should have learned this in year 12, really. Unless you didn't do it. Oh, do I have to explain? Yes! The thing that's most important is we're looking for everything beyond here. And so this actually is asymptotic, so it actually goes on forever. So just make sure in your upper bound, you just pick a really big number. Right, so that you cover everything. You don't want to cut this tail at any point. Okay. It is known that approximately half of New Zealand male youths who eat breakfast daily have an energy intake at breakfast between... Discuss whether the normal distribution presented above appears to be appropriate for modelling the energy intake at breakfast of New Zealand male used to eat breakfast daily. Is this also male use? Yeah. Okay. So there's an overlay. So they reckon that between two values, I'm just going to do it in red, 9,500 up until, what number was that? 12,000. I'm just going to put it down here. They reckon that that is known to be 0.5. So I think they want us to test that. So let's have a look. So let's just change our lower to 9,500 and our upper to being 12,000. Okay, so B2. So P that they are between 9,500 and 12,000 is equal to 0.4172, and that does not equal 0.5. Okay, let me read the question again. Discuss whether the normal distribution model presented above appears to be appropriate for modeling the energy intake at breakfast. Male use to eat breakfast daily. Okay. It seems that the model's standard deviation, I don't actually know how deep they want me to look into this, is, no, that's a big assumption. According to the model, around 42% of young males, or whatever the word they use, of young males are within the range which is significantly less than what is known to be true, in brackets 50%. Therefore, the model sucks, may be inappropriate. I love how you guys have to look at my horrible writing, but this is what we have to look at when we're marking it, so you know, tip the tat. I think that should cover that question. Pretty much what they really wanted was the calculation and then comparing the stat that they gave to the calculation, and then just that explanation doesn't really, as long as you've got the main points within that. Just saying that it's inappropriate is pretty much what they want you to do. Okay. Data is collected from students enrolled at single-sex boys school. At the school, 15% of youths who eat breakfast daily have an energy intake above 12,800 at breakfast. Suggest suitable values of the parameters, plural. So they're saying that M is unknown and standard deviation is unknown. That could be used for modelling energy intake at breakfast for male youths who eat breakfast daily at this particular school. Damn. Okay, this is a mean question, because pretty much all they're giving you is the fact that 15%, about that much, right, is above 12,800. But they are not giving you a mean and they are not giving you a standard deviation. So normally they would give you one of these and you can use that to work out the other with this information. But in this case, that's not even possible. So you have to guess one of those values. You're going to have to make up one of these values from scratch before you're able to do any algebra to find the other value. So this is a mean question. What we're going to do, I use this fact? It is known that approximately half of New Zealanders eat breakfast daily, have an energy intake between these two. What I'm going to do is I'm just going to pick the middle number of these. Because this... let's just pick a nice number, stuff them. There's nothing for us to go on. So I'm just going to pick whatever number's easiest for me to do blooming calculations on. Let's assume that the mean equals 10,000. Really easy number. Engineers love it. It's in the middle of what we were doing before. You should probably use some of the values that they were giving for these ones, but they haven't restricted you, so they can't remove marks for it, so I'll just pick the easiest number to work with. Shame. Okay, now, what you have to do for these is, this is where it's good to have learnt some table stuff, because in here, we can't do much else. So I'm going to put in mean equals 10,000 and standard deviation is unknown. These values here, this 15%, we can only get some data. So we know that equals X, but we're going to need to have a Z value because we need to use this formula. I'll probably get it up so you guys can see that. Where did I put my formula sheet? Oh, here it is. Go away. I want you. So on this formula sheet, I want this Z equals X minus mu over sigma. Okay, so Z equals X minus mu over sigma. So see how when we're doing it algebraically, we have a known X, so that's that covered. We have a known mean now, that's that covered. We need to find a Z, and then we can work out an unknown standard deviation. Pretty much in this formula, there are 4 unknowns. Anytime in algebra, when you have one equation, you can only have one unknown, right? So that's why we had to assume this. Tick that off. We have X, they gave us that, and we're going to need to find Z from a Z table, and then we'll be able to find our standard deviation. Okay, you could have also assumed a sigma and then use that to work out a mean, but this is probably just as straightforward. So what we can do is we can use Z to find out what 15%, what value 15% is on our Z distribution, because we know that Z has a mean of 1 and a sigma, mean of 0, sigma of 1. If you really wanted to troll them, you should pretty much pick your mean to be 0 kilojoules, and then it would make this super easy to answer. But we want to take it partially seriously, you know. What am I opening? Okay, so we could use our table for this, but that's for peasants, really. I'm going to use my calculator. So in our calculator, we want to know distribution, normal. We want inverse normal. I think we do. And we're going, it's a tail on the right. The area we're looking for is 0.15. The sigma, we're looking at Z. So sigma is 0, 1, and mean is 0. So now we have our, so it says X, but because we put in Z, this is actually a Z value, 1.0364. So now we have a Z, right? We were doing it inverse. I kind of want to explain this a little bit. The tail's on the right, the area we know, and because we're looking at Z, sigma is 1, mean is 0. So that's how we can find a Z value. Without using the table, we can just use our calculator. Okay, so now we know Z, 1.0364. We know our X, 12,800. This is my convenient mean that I selected. And then over sigma. We're trying to find an unknown sigma. It's going to take a little bit of algebra, but yeah, pretty much you multiply by sigma, so it's going to be 1.0364 times sigma. So all we're doing is, if it's, see, this just means a big divided by. And if it's a fraction, this is secretly also in brackets, so it needs to be done on its own. So to get rid of a divide by sigma, you just multiply both sides by sigma, so that disappears and it moves over here. 12,800 minus 10,000, I made that number nice, gives us 2,800. Now, all we need to do is get sigma by itself. So sigma is just going to be equal to 2,800 divided by. So if we just divide both sides by this number, it will get rid of it on the left side, 1.0364. So sigma is going to be equal to 2,701, oopsies, 0.6596. Sweet, that's all. So we've got a sigma value and we've got a mean value. Suggest suitable variables that could be used for modeling energy and take blah, 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 blah. Support your answer with statistical calculations and reasoning. Did I give reasoning? I don't know. If they don't give me the marks for that, maybe I'll check with the... I'm just going to quickly check the answers, because if I do that wrong... Yep, no, that's fine. Okay, cool. Question 3. How long is this video so far? An hour. Woo-hoo-hoo. Hopefully you guys are skipping and not listening to all of them. Okay. A common injury for sports players, which often requires surgery, is a ruptured anterior cruciate ligament, ACL. ACL surgery usually takes between 120 and 150 minutes, with the most common time being 130. Whenever you have a min, a max, and a mode, you know it's triangular. So it's a triangle here. So we got 120 and 150 with 130. So I'm going to draw, you don't have to draw a proportional triangle, but I do enjoy a good proportional triangle. Oopsies, I think I missed there. Does this make sense? I think I may have got it. No, 120, 150, and then 130. No, I think my diagram's a bit ugly, to be honest. This is way too long. Oh well. First thing I like to do with triangular is work out what the height is. We can go to our formula sheet for that. Yeah, if you're doing triangular, you may as well just learn how to use the formula sheet, because it's all on there. Let's make that nicely proportioned. Okay, so the height is 2 over b minus a. 2 over 150 minus 120. So it's 2 over 30, which is 1 over 15. And that is an ugly number, I think. 1 over 15. 0.07. But we're just going to use 1 over 15. So that's our height. Let's read the question. Using an appropriate distribution, calculate an estimate for the probability that a surgery takes less than 130. Oh, look at that, we already have a height there. So less than 130 is this area of the curve, not curve, the distribution. So Px is less than 130 equals the base. So it's half for a triangle's area, and look at this. This is the beauty of this distribution. You literally get given the area of a triangle calculation. As 18-year-olds, you get told how to work out the area of a flippin' triangle. Lovely. Half times base, so the base of this triangle is 130 minus 120, that's 10, times the height, which we worked out before, is 1 over 15. So that is 10 over 30, which is 1 over 3. Double checking that. Yes. Okay, so that is that question all done. 3AI. Okay, let's go to question 2 of that. Given that the ACL surgery takes less than 140 minutes, calculate an estimate for a probability that the surgery takes more than 130 minutes. Given that the surgery takes less than 140. Oh man, my picture's so ugly. It's so ugly, it's crazy. So this is 140 here. That's the worst triangle I've ever drawn in my life. Calculate an estimate for the probability that the surgery takes more than 130. So that's saying inside of, these are nice, I kind of want to colour in what they're actually asking here. So they're saying conditional on it being in this area here. Right, conditional on it being in this area, what is the chance that it's inside here? So this is a conditional question. They're asking us for the red out of the blue. So it's a conditional question. Bit sneaky. Man, it's so ugly to work out. I'm not keen on this. This is just like brute force. Anyway, let's do it. What we're going to need to do is we're going to need to find the area of this triangle, which we actually already know. So the P that it's between 130 and 150 equals 1 minus the P that it's less than 130. Right, so the area of this is just 1 minus the area of that, which we already worked out before. So that's 2 over 3. So that is going to be helpful. We're then going to have to work out the height here. So we want to work out that height. And that height is between, so this is C and this is B. So it's between C and B. So whenever you want to work out those heights, you need to use this formula here. Okay, so let's do it. Height at 140. I like calling out height because, yeah, just like calling out height. Height at 140. They use f of x, but that's a little confusing, introducing function notation to people doing distributions exams. 2b. Okay, I also like to label these because I get confused very easy. A is this one, B is this one, and C is this one. That's going to be helpful. Okay, 2 times B, which is 150, minus X, which is 140. Need a label on that as well. Over 150, which is B, minus A, which is 120. B, which is again 150, minus C, which is 130. Okay, calculator time. If you ever want to know how to work these out, it's a fun activity. Sadly, maths teachers find these things fun, or maybe it's just me. It's kind of fun working out where they got these from and doing like a little proof of how that the height of that triangle will be that calculation there. But yeah, I wouldn't worry about that too much. The important thing here is, see how I've put a bracket outside here and then a bracket at the end here? It's so that this fraction does itself in the right order. So I'm going to do another bracket on the bottom as well. 150 minus 120, bracket, 150 minus 130. Close that off. I think that should work. 1 over 30. Nice number. So the height here is 1 over 30. That's about right because this is 2 over 30. That's halfway up the triangle. Makes sense to me. So we've got the height at 140 now. So we can use that to work out this triangle's area. So at this point, I'm going to even start drawing mini triangles to keep in mind what I'm actually doing. Okay, so I'm working out this one here. So that's P 140 less than X less than 150 equals, so I'm going to get that base, half times 10 times, and we got this height before, 1 over 30. So that's 10 over 60 or 1 over 6. Is that right? Double checking. Yes. So we now know this area is 1 over 6. We also know that this area is 1 over 3. So therefore we can use that to find this area. That's just 1 minus 1 over 3 minus 1 over 6. Is that 1 over 2? Yep, that sounds about right. So we now know that that's half of the stuff is inside here. So now we can work out a probability. So we're actually going to do, what was the original question again? Takes less than 140. Calculate the estimated probability takes more than 130. So P, that it's between 130 and 140, given that it's between 120 and 140, is equal to this probability here, 130 and 140, we got that is half over, and we know that that is 1/3 plus a half. Right, so it's this area out of this area. Okay, let's do that. I'm going to be real careful with brackets. 1 over 2 over 1 over 3 plus 1 over 2. Is that good? Yes. 3 over 5. I feel like I should check that, because if I'm wrong, that will be... Yep, that's right. That gives you an excellence, because it's got conditional probability and a fairly complicated version of triangular distribution. Okay, moving on. 3B I. They want us to find the mean and standard deviation of the number of repairs. Oh, see, I should probably read this. The hospital is considering sourcing a new X-ray machine. The table below shows the probability distribution of a random variable n, the number of repairs needed for an X-ray machine over any 3-year period, to calculate the mean and standard deviation. So we've got a table. I use the calculator for this. You have a formula sheet. Alright, so you got this formula sheet here. So you could find, oh, it's actually just straight up, I'm pretty sure. No. You could use these calculations to do it, but they are a mission. They are not worth the achieve grade that you get for these. So I use a calculator. You go into stat and you just make up lists. So you put n in the first list, 0, 1, 2, 3, and you go over and you go 0.11, 0.34, 0.35, 0.2. Then what you want to do is you want to calculate, and it's one variable, but we need to set first. So the list is in list 1, yeah, that's what we did, and then the frequency of each thing happening is in list 2. Nice. So then we just go 1 var, and it will tell us here is our, so x bar is one way of saying mean, so it's 1.64 mu equals 1.64, and standard deviation is just zone down here, 0.922, 0.9222. Yeah, that's a way easier way of doing it. Okay, question 2. Hospital is considering leasing an X-ray machine from company A or company B. A charges a one-off fee of split with an additional $350 per month. B charges a one-off fee of blip with an additional $10,000 per repair. Discuss which company has the higher variation in total lease costs over the 3-year period. Well, company A has 0 variation. Oh, no, it doesn't. That's not true. That's not true. Yeah, it is true. It has 0 variation, whereas company B charges per repair, so has variation. And what was the question? Discuss which company has the higher variation. So, company B has higher variation. I don't know if that's a dumb question or I'm giving a dumb answer. No, yeah, no, that's what they want. Weird. Okay, well, that was... This is the last question. Oh, damn, we're on the last question! Okay, cool. Question 3. Okay. The hospital will lease an X-ray machine for 3 years. From which company would you recommend the hospital lease the X-ray machine? Company. Is the company a hospital? Okay, so they're a hospital. What does their accountant want in a hospital? They want. Okay, we'll find out. Okay, so let's work out company A. Expected value. Expected value of company A is going to be the amount of repairs. Wait, okay, one-off fee equals 69,500. Right, that's what they have to pay that fee. Plus, and they're doing it for 3 years. Plus 3 years times 12 months times 350. That's easy. $69,500 plus 3 times 12 times 350. Yeah, that's what they're going to be paying. So that X-ray machine is going to cost them $82,100 for lease. Okay, now the expected company B equals $65,000 plus 10,000 per repair. 10,000 times, and we have an expected value. We got that before. We know the amount of repairs is going to be 1.64. 1.64 on average. We're just doing an expected value, so we can do that. And we will find out which one has a 65,000 plus 10. Oh, why am I doing? Are you serious? I'm doing this on a calculator. It's the last question I'm allowed to. Times 1.64. This is an embarrassing calculation to type in. 81,400. Company A is company B is expected to be cheaper than company A. And what is the question again? The question is saying you recommend. The difference is this is an insignificant difference though. Significant difference of what? What is the difference here? It's tiny, right? $700 or something? Of $700 though. And company B, company and company A, company B has variation, which a hospital might not want. in cost, which will make it harder for the finance department, or something like that, to allocate money. Right, do they want me to work out the variation? I could work out the variation because we have a standard deviation that we can work with, but I don't think that they care too much. Yeah, yeah. I would select company A. Select company A for its lack of variation. An insignificant increase. Yeah, I would do that. You could work out what that variation is going to be because we know the distribution from here, that we have a standard deviation, and we could see that maybe there's 0 repairs, maybe there's up to 3 repairs. So you could work out if there's 0 repairs, right? It's going to be just 65 grand. Oh yeah, we can do that. 65 grand, but then 2, and then there could be 3 repairs. So if there were 3 repairs, it would cost 30 grand extra, so it would become 95 grand. Right? If there were 0 repairs, it's going to cost that, and if there's 3 repairs, it's 95 grand. And that, I think that variation is not worth the $700 in saving, because you might have to pay 95 grand, and if they are the ones doing the repairs and everything, they might give you some dud machine that has this false repair. I don't know. I wouldn't trust the company for $700 in savings. Okay, so that has been the 2020 distributions paper. I hope you learned something, and that's it. Thank you for watching. If you made it this far, and if you're still listening to me, then you're actually crazy. Ka kite anō!